So, limit rules, the sum rule, the difference rule, the product rule, and the quotient rule for limits, all guarantee that basic algebraic formulas, formulas that only involve those operations, are continuous on their domains. So if I have a limit of a formula, for example, x squared minus 3x, if I were to look at the graph, because it's continuous, all I need to do is look at the value of my function, which means all I need to do is plug in my x value into my formula. So I get 4 minus 6. I get a value of negative 2. The function value and the limit are the same. It works for fractions as well. So for example, if I want the limit as x approaches 1 of the function x minus 3 over x plus 1, because that formula is continuous, I can just plug in 1. 1 minus 3 over 1 plus 1. Negative 2 over 2 is negative 1. That's another example where my function is continuous. On the other hand, if I use the same function, but I approach x equals negative 1, if I think about what happens when I plug that in, I cannot use the value of the function at negative 1 because my function does not exist. That fraction involves division by 0. It's not defined. When a limit is looking at the value of a function where the function is not defined, we need to use our algebra to decide if there's another function that is continuous that we can find a limit of. When you evaluate the function and you find that the formula looks like 0 over 0, it has a chance of being rewritten. We call such limits indeterminate form. When you evaluate a fraction and it has a form L over 0, where the numerator is non-zero, there's absolutely no chance that you can find a new function. Instead, this corresponds to a spot where the function has a vertical asymptote, which means we have an infinite limit. To illustrate the first example, imagine the function x squared minus 1 over x minus 1. 1's clearly not in the domain, but if I plug in 1 into my formula, I get 1 squared minus 1 on top, that's 0, over 1 minus 1, that's 0. I have a 0 over 0 form. It's indeterminate. I have a chance. This will require some additional algebra. Notice, by the way, that I did not use an equal sign. I used an arrow. This is because I can't say that these numbers actually exist. Instead, I'm just simply saying that the limits have a form where the top goes to 0 and the bottom goes to 0. For these algebraic problems, our approach for rewriting it is to use algebra by factoring. So we see that x minus 1 is a common factor. It would cancel, and I can, instead of computing the original formula, I can compute the limit of another function, x plus 1, as x approaches 1. This function is defined at 1, and so it must equal the value of the function. 1 plus 1 equals 2. The limit of the original function is the same as the limit of x plus 1, which is the number 2. Notice, by the way, I continue to write the limit next to my formula because I'm computing a limit in each of these cases. As soon as I stop my formula and I substitute x goes to 1, I stop writing the limit. To illustrate an example of a limit that does not exist, let's look at the function x squared minus 3x over x minus 2 at the point 2. If I imagine what happens at x equals 2, the top goes to 2 squared minus 3 times 2. The bottom goes to 2 minus 2. So I get on the top negative 2, on the bottom 0. This function has no chance. The graph of this function has a vertical asymptote. There's no limit. Piecewise functions correspond to the picture we had in our second example of the spaceships, where my function had one curve on the left and a different curve on the right, and we need to calculate the limit from both sides. So for example, a piecewise function might look like f of x equals, curly brace means I have to make a choice. Let's do x squared if x is less than 1. And how about we do 2 if x equals 1, and 3x minus 1 if x is greater than 1. So if I were to take a limit, algebraically what I do is I need to think about the two sides. I'm interested in the limit as x approaches 1 from the right of my function. To say that x is approaching 1 from the right means that x is actually greater than 1. And so I'm using the third rule. My function gets replaced by the formula 3x minus 1. That happens to be a continuous formula, so I get to plug my 1 in. I get a value 2. If I'm looking at the limit of my function from the left, this means that x is less than 1. My function gets replaced by x squared. By the way, this minus sign on the 1 does not mean negative, it simply means left side. X squared is a nice continuous function, so I get to plug in my formula. 1 squared equals 1. The limit on my left is 1, the limit on my right is 2. Notice, by the way, that we never use what happens at x equals 1 for limits. If I thought about my actual graph, what this says is that for all the x values that are less than 1, I use the formula x squared. And so my graph looks like the y equals x squared graph. On the other hand, for all of the x values greater than 1, I use the formula 3x minus 1. And so my function looks like the line y equals 3x minus 1. The limits that I found were showing that if I were to follow the y equals x squared graph from the left and approaching 1, I go to a point with a height of 1. If I approach from the right, I end up following down the line and I get a value of 2. Now, the point that is actually that I said I never use for limits corresponds to the actual point. In this example, my function is right continuous because the limit from the right agrees with the function. So that's a visual idea of how limits work.